In probability theory and statistics, a probability mass function is a function that gives the probability that a discrete random variable is exactly equal to some value. The probability mass function is often the primary means of defining a discrete probability distribution, and such functions exist for either scalar or multivariate random variables whose domain is discrete. A probability mass function differs from a probability density function in that the latter is associated with continuous rather than discrete random variables. The values of the latter are not probabilities as such. A PDF must be integrated over an interval to yield a probability. Formal definition. Suppose that x, SA is a discrete random variable defined on a sample space S. Then the probability mass function fx 0, 1 for x is defined as thinking of probability as mass helps to avoid mistakes since the physical mass is conserved as is the total probability for all hypothetical outcomes x. When there is a natural order among the hypotheses x, it may be convenient to assign numerical values to them and to consider also values not in the image of x. That is, fx may be defined for all real numbers and fx equals 0 for all x. X is shown in the figure. Since the image of x is countable, the probability mass function fx is 0 for all but a countable number of values of x. The discontinuity of probability mass functions is related to the fact that the cumulative distribution function of a discrete random variable is also discontinuous. Where it is differentiable, the derivative is 0, just as the probability mass function is 0 at all such points. Measure theoretic formulation. A probability mass function of a discrete random variable x can be seen as a special case of two more general measure theoretic constructions: the distribution of x and the probability density function of x with respect to the counting measure. We make this more precise below. Suppose that is a probability space and that is a measurable space whose underlying sigma algebra is discrete, so in particular contains singleton sets of B. In this setting, a random variable is discrete provided its image is a countable set. The push-forward measure, called a distribution of x in this context, is a probability measure on B whose restriction to singleton sets induces a probability mass function since for each B in B. Now suppose that is a measure space equipped with the counting measure mu. The probability density function f of x with respect to the counting measure, if it exists, is the Radon-Nikodym derivative of the push-forward measure of x, so an f is a function from B to the non-negative rails. As a consequence, for any B in B we have demonstrating that f is in fact a probability mass function. Examples. Suppose that S is the sample space of all outcomes of a single toss of a fair coin, and x is the random variable defined on S assigning 0 to tails and 1 to heads. Since the coin is fair, the probability mass function is this is a special case of the binomial distribution, the Bernoulli distribution, an example of a multivariate discrete distribution, and of its probability mass function, is provided by the multinomial distribution.